Numbers every LLM developer should know. So this is a cheat sheet from Ray project. Okay. So if you want to read through this particular GitHub page, you can skip the video or you can continue the video for my explanation over here. So here, if you look at these numbers, so the first section is prompts. Okay. They say 40 to 90% amount can be saved. Basically, cost can be saved by appending be concise to your prompt. So the idea is that you pay for the tokens which have been generated as part of responses from large language model. So you can ask the large language model to be concise by adding be concise word to your prompt, thereby reducing the number of tokens that is generated. Okay, in this way you can save up to 40 to 90% of cost. Okay, then the next term over here is 1.3 average tokens per word. So the idea is that large language models operate on tokens, right? Tokens are words or subpart of words. So a 750 word document in English will be close to 1000 tokens. For languages other than English, this could increase, right? So a word like eating might be broken into two words, eat and ink. So this is a typical number. Okay, average tokens per word. So if you have 750 word document, you can have close to 1000 tokens. Knowing this ratio is important because most billing is done in tokens, and the LLM's context window size is also defined in tokens. Okay, so this is about prompts, right? Then you have about price. Okay, so the cost ratio of GPT-4 to GPT 3.5 turbo is almost 50, right? So what this means is that it is much better to use GPT-4 for things like generation and then use the data to fine tune a smaller model. It is roughly 50 times cheaper to use GPT 3.5 turbo rather than GPT-4. Okay. The roughly is because GPT-4 charges differently for the prompt and the generated output. So you need to check how far you can get with GPT 3.5 turbo. So GPT 3.5 turbo is 50 times cheaper than GPT-4. Okay. The next cost ratio is 5. Cost ratio of generation of text using GPT 3.5 turbo versus OpenAI embedding. Okay, this means it is way cheaper to look something up in a vector store than ask LLM to generate it. Okay, so you can use embeddings to look up rather than use GPT 3.5 turbo to generate. Okay, so the cost difference compared to GPT-4 is a whopping 250x. So if you are looking at information retrieval system, if you use OpenAI embedding, it could be 5x less than if you use GPT 3.5 turbo. That is the idea over here. Okay. Then 10 is the cost ratio of OpenAI embedding to self-hosted embedding. So OpenAI embedding would be 10 times expensive than your own embedding. Okay. This number is sensitive to load and embedding batch size. So we noted that using a particular instance G4DN.4x were able to embed about 900 tokens per second using Hugging Face sentence transformers, which are pretty as much as good as OpenAI embeddings. So doing some basic math of that rate and the node type, it is considerably cheaper by a factor of 10 to self-host embeddings compared to OpenAI embedding. Okay. The next is cost ratio of OpenAI base versus fine-tuned model queries. So again, it costs you 6 times as much to serve a fine-tuned model as it does the base model on OpenAI. This is pretty exorbitant but might make sense because of the possible multi-tenants of base models. It also means it is more cost effective to tweak the prompt for a base model than to fine-tune a customized model. So fine-tuning customized model is expensive. Okay. So cost ratio of self-hosted base versus fine-tuned model queries is 1. So if you are self-hosting a model, it more or less costs the same amount to serve a fine-tuned model as it does to serve a base one. The models have the same number of parameters. Okay, so that is this cost, right? Now if you go to training and fine-tuning, so what they say is that if you were to fine-tune, right, or train, right, so basically this is training a 13 billion parameter model on 1.4 trillion tokens, is close to $1 million, right? So the Llama paper mentions it took them 21 days to train Llama using 2048 GPUs, A180 GPUs. So if you are to consider these numbers and then train your own model on Red Pajama training set, then they say that considering that you want to train on this much hardware, it would take close to $1 million. That's what they're saying over here, right? Then you have the cost ratio of fine tuning versus training from scratch, right, which is less than 0.001. So what does it mean? Okay, but the cost of fine tuning is negligible. That is what they are saying. It could this is a bit of generalization. So they show an example where you can fine tune a 6 billion parameter model for about $7. Even at OpenAI's rate for its most expensive fine-tunable model DaVinci, it is 3 cents per 1000 tokens. This means to fine-tune on entire works of Shakespeare, you are looking at $40. But however, fine-tuning is one thing and training from scratch is another. Okay, so that is the idea. Fine-tuning is going to be cheaper rather than training from scratch. Okay, then they talk about GPU memory. Right, so typical GPU memory requirements of an LLM for serving are 2x number of parameters. So the idea is that if you have a 7 billion parameter model, you would require at least 14 GB of GPU memory. Okay, and these are various GPU memory capacities of various graphics cards, right? So their VRAM capacities are different cards have different capacities. And then this will cap the number of parameters your large language model can serve, because based on this particular thing, if you have a 7 billion parameter model, it could take up to 14 GB of GPU space, right? So depending upon the parameter model parameters, you might need to go for the different graphics card capacities, and based on that they have costs associated with it, right? So the idea over here is that this is because you can go for 16-bit float per parameter. You need not go for much higher accuracy for the parameters. You can also go to 8-bit accuracy. You might start to lose resolution, but it could be acceptable in some cases. Then there are some efforts like Llama CPP, which runs a 13 billion parameter model on 6 GB CPU by quantizing aggressively to 4 bits, but it is atypical. So typically, this is the number, 2x number of parameters, okay, for serving a LLM. This is GPU memory, okay. So typical GPU memory requirements for an embedding model is less than 1 GB. That's what they are saying over here. Typical GPU memory requirements of embedding models. Embedding models are much smaller. So typically it's almost close to a 1 GB, okay, of GPU memory. So throughput require improvement from batching LLM requests. So basically LLM requests are to GPU is very high latency running LLM query. So it may take 5 seconds with a throughput of 0.2 queries per second. Okay. If you run 2 tasks, it might only take 5.2 seconds. That means that if you can bundle 25 queries together, it would take about 10 seconds and your throughput improves. But it again depends on the amount of GPU memory required for a token, the batch size basically, right? What they say is that the amount of memory you need is directly proportional to the maximum number of tokens you want to generate. If you want to generate outputs of up to 512 tokens, about 380 words, you need 512 MB of GPU memory. But if you have 24 GB to spare, that is fine, okay? But if you want to run bigger batches, it starts to add up. So if you need batches of 16, you would need 8 GB of space. So batch, so these two are related to each other. Throughput improvement is possible from batching, but it is constrained by the GPU memory. Okay, so all these numbers are present in this particular sheet. So you could actually check out them. So they also have this particular link where you can check how they have calculated these numbers. So this is very useful for every LLM developer. I'll be putting the link of this sheet and this GitHub page. You can check it out. I hope this video is useful for you. If you like the video, please like, share, subscribe to the channel. See you in another video.